Hi folks, welcome back to Math with Captain Rod. The purpose of this video here is to discuss what are called volumes of revolution. We're going to talk about what they are and second, how they're calculated. So we're going to look at the function y equals 2x plus 1. I like to use very simple functions when I introduce new concepts here. And we're just going to look at it out to the point where x equals 2. That would make this the point 2, 2. So we're just going to look in the region from 0 to 2 here. All right, now, first thing to realize is that, mathematically, there is some sort of area bound here within this region. And if we were to take this whole entire area and rotate it about the x-axis, we would get a geometry. We would get a three-dimensional geometry. And I'm going to sketch, what that geometry would look like. It would look something like this. All right, now, this is the point 0, 2. So this circular surface here would have a radius of 2. This circular surface on the right here would have a radius of 4. And I'm getting that from the function value here. And what we're going to do here, the purpose of this video is to learn, all right, how do we calculate the volume of this geometry? How do we calculate this thing's volume? Now, hopefully you've seen my video on how to calculate surface areas. Well, we're going to start this with a similar concept here. I'm going to start by drawing a differential element, a rectangle. Now, whether or not the rectangle goes vertical or horizontal is kind of your choice. I'm going to start this with a vertical rectangle. This rectangle has a length, that would be this distance, equal to the function value, which in this case is 2 plus x. Its width, we could label it as a delta x or a dx, depending on our intention and how we're going to work it. I'm going to work this using integration. So I'm going to go ahead and say that this area here has a length equal to 2 plus x and a width equal to dx. Now, what you have to imagine now is the area of this rectangle. If I were to take this area and revolve it about the x-axis. Very important thing to realize, which is why I'll leave this in red, the geometry that you're going to get is going to look like a penny or a dime or something. It's going to look something like this. The important thing to be able to do is go from this picture to this picture and label the geometry here. The thickness of this dime or this disc would be dx. It's going to be whatever we labeled this as. Now, this is a circular area. Anytime you're dealing with circles, the radius is going to be important. The radius is equal to this distance, which is the function value, y, or we could just put 2 plus x. Now, in this picture, like in our original volume, what we have is we've got like one of these. We've got like a little slice of it, basically. And what we want to do is write an equation for the volume of that slice and then add them all up with the integral process. I'm going to do that right now. The volume of this element would be dv. Now, the reason I write it as dv, if this is a dx, that means this thing's infinitely thin. So it's got a differential thickness, therefore it's a differential volume. If I take this surface area and multiply by the thickness, I would get this thing's volume. And because it's a circle, its surface area is pi r squared, or pi times 2 plus x squared. I'll go ahead and sub that in next time around. So pi r squared times the thickness, dx, gives a volume. The total volume, then, we would get by adding these all up. So we're going to integrate, and since I'm looking here, we're integrating with respect to x. X is starting at 0 and going to 2. So we're going to have integral 0 to 2 of pi r squared. Now I'm going to look here. R is equal to 2 plus x. And again, that's being squared times dx. So what we've done now is set up an integral that will tell us the volume of that region. And now I'm going to go ahead and evaluate it. So this is going to equal. Now the pi can come out in front. I guess I'll go ahead and do a little bit of work here. 0 to 2. If we take the 2 plus x and square it, That's going to be 4 plus 2x plus x squared. And again, it's not just equal to 2 squared plus x squared. You have to FOIL that. 2 plus x times 2 plus x. And now we'll just do this term by term. So the integral of 4 dx is 4x. The integral of 2x dx is 2x squared over 2. That's going to be just x squared. The 2's will cancel. Then the integral of x squared dx is x to the third over 3. Kind of running out of room, but that's evaluated from 0 to 2. That's going to equal pi times 4 times 2 plus 2 squared plus 2 cubed over 3 minus 0 plus 0 plus 0. Writing it all out. I'm going to take a moment and pause this while well, actually, no, we don't need to pause it for this, right? So what do we got? 8 and 4 is 12. And 8 thirds. So let me just give me a decimal for 12 plus 8 thirds times pi. Got a helpers going here, but they're waking up here. It's Monday morning. $13.6. All right, looks like this is approximately 13.6. This is a volume, so I'm just going to put CU, which stands for cubic units. And hopefully that's right. If it's not, it's their fault. All right. So, the important points here. One, recognizing what happens when you revolve this surface area, all of it, about the x-axis here. We get a geometry that looks like this. Now, there's nothing special about the x-axis. I chose it as an example. We could have revolved this geometry about the y-axis or about x equals 2 or any, there's a whole bunch of axes we could choose. I just happen to choose one that's kind of easy to demonstrate concept. The important thing is choosing an element, revolving it about the axis like I did, and that's going to give us this disk. For this reason, this is usually called the disk method when you look in your textbook here. You need to be able to write down something for the geometry of the disk. You need to be able to figure out its radius and its thickness and label them. Then you write out some sort of formula or equation here for your element. And then the process of integration gives us the entire volume. So what you have to envision here is that this represents the volume of one little slice of this in here somewhere. And then the integral adds them all up. Now, there's multiple ways to work this problem. I think what I'm going to do here is I'm going to pause this for a moment and clean it up and talk about method number 2. All right, folks, I'm back. I made myself some more room here, and I'm going to talk about an alternate setup to this problem. Again, same question, same problem. What if we took this trapezoid here, revolved it about the x-axis? We'd get this geometry. And what are the different ways to calculate this thing's volume? So I talked about what it looks like if we use a vertical rectangle. We'll talk about what it looks like if we use a horizontal rectangle. Oops, I guess I'm not going to need this anymore. So it's perfectly acceptable to draw a horizontal rectangle for this problem. Go ahead and draw this in red. But it's important to realize, all right, I'm going to draw two of them. I'm going to draw one here and another one here. When we start talking geometry of this rectangle, this distance is a dy now. It's a vertical distance. I'm imagining that thing's infinitely small. Same thing with this little rectangle right here, dy. When we set up the equation for the volume, we're going to need the length of the rectangle. Now, there's an important thing to realize, right? This rectangle here, and you have to imagine it moving up a little bit or down a little bit. Its length does not change. That first rectangle has a length equal to 2. However, once we get above this point, the length of the rectangle starts varying now. Now it's a function. The length of this rectangle is going to be this distance, which is 2, minus this distance, which is x. So the length of this rectangle is going to equal 2 minus x. And again, it's very important to understand why. I'm going to go over that again. Right, in this picture, from here to here is 2. From here to here is x. The distance we want here in green is that distance, which would be 2 minus x. All right. Now, when we take either of these rectangles, and I'm just going to do one of them, it doesn't matter which, and revolve it about the x-axis, what we're going to get is a geometry that's going to look like this. It's going to look a little bit like a can. It's very important to realize that this geometry is hollow because we're revolving only this area about the x-axis. Again, this is going to come around like this. It's going to give us this kind of can-looking geometry, but it's very important to realize that this is hollow in here. There's nothing inside of there, right? This dimension right there, like the thickness of that side, right, is the width of this rectangle. That's dy. This dimension right here is going to depend on which rectangle we're talking about. If we're talking about this guy, it's 2 minus x. If we're talking about this rectangle, it's 2, constant. Now I'm going to talk about how to set up the volume equation for this, and then I'll talk about how to set the integral up. Now, if you were to take this and cut it and unfold it, it would basically be a rectangle now. It would look like this. I've exaggerated the thickness of it, though, greatly. This length is the 2 minus x, or the 2, depending on which one of these rectangles we're talking about. The thickness, like this dimension this way, is the dy. And here's a really important part. The length here is one circumference, 2 pi r. So, and again, this dimension right here is the same as this. It's 2 minus x or 2, depending on which of these rectangles we're thinking about. Now the radius is this distance, which is equal to the function value, y. So this is equal to 2 pi y. Now what we can do is just write an expression for the volume of this. dv is going to equal, right, the length, 2 pi y, right, so that's this dimension, times this dimension. Now that's going to be a 2 minus x or a 2, depending on where you're talking about. Now, because the length of the rectangle changes how it's defined at this point, if you set it up like this, it's required that we write 2 different integrals to solve this problem. So what I'm going to do here is I'm actually just going to go back and write this in integral form here. I'm going to just get rid of the dv and write v equals. Okay, so 2 pi y is this dimension times this dimension, and I'm going to do for the first rectangle, so that's going to be times 2 times this dimension dy. This expression added up as y goes from 0 to 2 is going to give us the volume of the interior, the first part. Then we're just going to add a new expression where we're going to integrate with respect to y from 2 to 4. And it's going to be very similar. Okay, length, 2 pi y, times this dimension, but now we're talking about this rectangle, whose length is equal to 2 minus x. I'll just leave that for now. And then times the thickness, dy. Right? This can now be integrated to find the volume, and right here for this, to deal with this 2 minus x, if I solve this for x, I get y minus 2, if I look right here. So what we can do is we can put y minus 2 right there for x, and then just go through and work both integrals, integral 1, integral 2. I'm going to save that as an exercise to the video person watching this. This should end up being the same as our setup before. As you can see, though, it's quite a bit more work. It's longer, it's a bit more complex looking. So this method's called the shell method, because this thing that I've kind of designed here by taking this element and revolving it about the x-axis is a shell, or what we call a shell. Sometimes the shell method will yield an easier looking result, sometimes the disk method, and you have to know how to do both. So anyway, I hope this video helps demonstrate how to set up integrals to calculate volumes. Have a great day.